In this section, we will learn about thiols. Thiols are analogous to alcohols. As we know, alcohol functional group is OH, also known as hydroxyl group. In thiols, the functional group is SH, and this functional group is also known as sulfhydryl group. Remember, oxygen and sulfur are present in same group of the periodic table. Hence, the chemical properties or other physical properties of oxygen and sulfur atoms are quite similar. Therefore, there are many similarities between thiols and alcohols. A ball and stick model of a thiol compound, methyl thiol to be exact, is shown here. As we can see in this ball and stick model, the bond angle around the sulfur atom is 103 degrees. We know that this carbon atom is sp3 hybridized, and in sp3 hybridized molecules, the bond angles are 109.5 degrees. In alcohol, the bond angle around oxygen atom is approximately 109 degrees. So therefore, in alcohol, the oxygen atom is said to be in sp3 hybridized state, where two of the sp3 hybrid orbitals contain the lone pair. The other two are used to make the bonds with hydrogen and carbon. So if in thiols, this sulfur atom is also sp3, then the bond angle around the sulfur atom should be about 109.5 degrees. Let's say 109 degrees. And if sulfur is not hybridized at all and it only uses its p orbital to make these bonds, then the bond angle, so these are the p orbitals. So if the bonds are made with the help of p orbitals, then this bond angle would have been 90 degrees. Now the actual bond angle in the sulfhydryl group is 103 degrees. So it's neither pure p orbital nor it is pure sp3 hybrid orbital. So what we can say is that the hybridization state around the sulfur is somewhere between the pure p and sp3, or we can say that it has more p character in the hybrid orbitals because the bond angles are not close to the actual sp3 hybrid bond angles. It is closer towards p orbital bond angles, which is 90 degrees. So therefore we can say that there is considerably more p character in the bonding orbitals of sulfur atom. Before the IUPAC system, thiols were known as mercaptans. The name mercaptan came from mercury capturing compound. So meaning of mercaptan is mercury capturing. They were given the name mercaptan because thiols would react with the mercury compounds and they will precipitate out as salts, water insoluble salts of mercury. So essentially they would capture the mercury, and hence the name mercaptan was given to them. So sometimes this mercaptan name is still used in mercaptan name terminology. We write the name of alkyl group followed by the word mercaptan. For example, if we have an ethyl group with SH connected to it, so then the name would be ethyl mercaptan. According to IUPAC rules, the names of thiols are quite similar to how we name regular alcohols. There is one modification. So all the rules which we apply to the nomenclature of alcohols are still applicable to the nomenclature of thiol. Essentially, we find the longest chain, and the parent chain name came from the longest chain. For example, in this first example, the longest chain is 4 carbon long, and so we write the parent alkane name. In alcohols, we remove the E and then we add ol at the end in case of alcohols. However, in thiols, we do not remove the E at the end. We keep the E and we simply write thiol at the end. So the name of this compound is butane thiol. And of course, we need to identify the location of the sulfhydryl group. So the parent chain is numbered from the side, which gives the functional group the lowest number. So in this case, we number from the right hand side, so it would be 1, 2, 3, and 4. So thiol group is at number 1 position, so name will be 1-butane thiol. In second example, again we number from the side where thiol group gets the lowest number, so that would be 1, 2, and 3, and we can see there is a methyl group at number 2 position, so name of this compound will be 2-methyl 1-propane. Remember, we do not remove the E, and then thiol, so 2-methyl 3-propane thiol. When other functional groups are also present, such as alcohol, then the thiol group is treated as a substituent, and in that case, it is called sulfonyl. So, for example, the name of this compound is 2-sulfonyl ethanol. The electronegativity value of sulfur is about 2.5. which is quite close to the electronegativity value of hydrogen. Because of similarity in the electronegativity values of sulfur and hydrogen, the SH bond is not polar, and therefore thiols show very little association by hydrogen bonding. Because of lack of hydrogen bonding or other stronger intramolecular forces, thiols have lower boiling points and they are less soluble in water than alcohols of comparable molecular weight. The boiling points of various common thiols and alcohols are compared in this table, and as you can see that the difference in boiling point between thiols and alcohols is quite a lot. In fact, boiling points of thiols and its constitutional isomer dimethyl sulfide is almost similar. Dimethyl sulfides are analogous to ethers. Between ethanol and dimethyl ether, the boiling point difference is huge. However, in case of sulfur, the boiling point is almost identical. This proves that thiols have almost no hydrogen bonding at all. One of the most characteristic physical property of low molecular weight thiols is their stench. The scent of skunks is primarily the result of these two thiols. All low molecular weight thiols are bad smelling compounds. A blend of low molecular weight thiol is added to natural gas as an odorant. It is added to detect any leaks because natural gas by itself is odorless. The two most common compounds which are added to natural gas for odor is 2-methyl 2-propane thiol and 2-propane thiol. Thiols can be easily prepared by nucleophilic substitution reactions using alkyl halide as substrates and hydrosulfide ion as a nucleophile. We know that SH ion or hydrosulfide ion uh, is an extremely strong nucleophile, and it will undergo SN2 type of mechanism, and it will replace the halide ion, where halide ion will leave, and it would result in the formation of a thiol. These kind of reactions work the best if our substrate is primary, as in this case of 1-iododecane. Secondary substrates do not work as well. Their rate of reaction is slow, and there will be a competing elimination reaction in secondary substrates. In tertiary substrate, this preparation of tertiary thiol is not feasible because in tertiary substrate, elimination reaction predominates and nucleophilic substitution does not take place. So therefore, this method of preparation works only for primary and secondary alkyl halides. One of the commercially important reaction in which thiols are prepared is shown here. In this case, sodium hydrosulfide is the source of nucleophile, and our substrate is sodium iodoacetate, and this reaction gives us a product called sodium mercaptoacetate or sodium thioglycolate. This compound, sodium thioglycolate, is used in cold waving of hair. Or in other words, this compound is used as a chemical which can straighten up the curly hairs. This compound works by breaking the disulfide bonds which are present in the protein molecules in hairs, and thus it removes the curly character of those proteins, and therefore the hairs become straight. Another method of hair straightening is by heat. However, with this chemical straightening using this compound, there is no need to heat. So therefore, this kind of procedure is known as cold waving of hairs. Thiols are stronger acids than alcohols. The pKa values of a thiol is about 10, and pKa values of most of a small molecular weight alcohol is about 16. The strong acidity of thiol can be attributed to the stable conjugate base, because sulfur is a larger atom than the oxygen atom. So due to the larger size, the sulfur atom can hold the negative charge, and hence this resulting conjugate base is more stable, which would mean that the acid from which this conjugate base came from is more stronger. Thiols are sufficiently strong acids so that when they are dissolved in aqueous sodium hydroxide, they are converted completely into alkyl sulfide ions. This kind of reaction is not feasible in most alcohols. To name the salt of thiols, give the name of cation first, which is sodium in this case, and then followed by the name of alkyl chain uh, or alkyl group. In this case is ethyl, and then uh, attach the suffix sulfide. So name of this salt is sodium ethyl sulfide. Most of the chemical properties of thiols are due to the fact that the sulfur atom of thiol is oxidized easily to several higher oxidation states. The most common of these oxidation uh, processes are shown here. A thiol can be oxidized to a disulfide, or it can also be oxidized to sulfenic acid, and further oxidation of sulfenic acid will result in formation of sulfonic acid. In all these various compounds, the oxidation states of sulfur is different, and oxidation state is lowest in thiol, and all the compounds in the product side, they have higher oxidation states. Many compounds with other oxidation states of sulfur are also possible, but they are not very stable. So these three kind of compounds are the most stable oxidation products of a thiol. It should be noted that in thiol and in disulfide, sulfur atoms have 8 electrons around them, or in other words, their octet is complete. However, there are 10 electrons around sulfur atom in sulfenic acid and 12 electrons in sulfonic acid, or 12 electrons around sulfur atom in sulfonic acid. So it is well documented that sulfur atom do show expanded octets in many of its compounds, and these two compounds are a couple of such examples. The most common oxidation reduction reaction of sulfur compound in biological system is the interconversion between a thiol and a disulfide. Thiols are oxidized into disulfide by molecular oxygen in biological system. Thiols are so reactive towards oxidation with molecular oxygen that they must be protected, or they must be protected from coming in contact with oxygen while storage. This disulfide bond is an important feature which stabilizes the tertiary structure of many proteins. So hence this reaction is one of the most important biological reaction. With that, we conclude chapter number 10. In this chapter, we learned about alcohols. We learned about physical and chemical properties of alcohols. We discussed reactions of alcohols, including dehydration and oxidation. And also we learned about thiols. We discussed the various physical properties of thiols, and we also learned about oxidation reactions of thiols. Thank you everyone for watching the video. If you have any question, please let me know. Have a wonderful rest of the day. Bye bye.